Okay, hello again everybody. Today we are going to be talking about another reaction of alcohols. In this case, it's a reaction, quite a common reaction of alcohols to make ethers, hence the name ether synthesis. The name Williamson is just the name of the guy that discovered this reaction. In fact, you'll see throughout Organic 2 there are a whole bunch of reactions that bear the names of the people that discovered them, so just an FYI. So let's actually take a look at this reaction here. You can see it appears to be two steps. One is sodium hydride, which you may have seen before. If you remember, sodium hydride is actually, let me draw it here, is actually H minus. So essentially a negatively charged hydrogen. And that, in this case, is going to act as a base. So if it's going to act as a base, what do you think it's going to remove? You remember bases attack hydrogens. And what's the most acidic hydrogen in this molecule? Well, hopefully you'll see it's this hydrogen connected to the oxygen right here. So therefore, the sodium hydride, literally all it does is it grabs that hydrogen, and in doing so, breaks that bond and puts those electrons onto the oxygen. And when that happens, what we get out here is a species that we have seen before. It's essentially a species that's a nucleophilic oxygen called an alkoxide. So this negative charge says this oxygen is unhappy, it wants to go find something to bond with. And if you look at the structure of our product here, you will notice that there are two carbons here that we somehow need to add in. If this is our nucleophile, then we need something that's going to be our electrophile. And if you remember from your SN1, SN2 time back in Organic 1, you will remember that electrophiles are things that have good leaving groups. And good leaving groups would be, well, let's see some examples of good leaving groups. Well, halides, for example, bromine, chlorine, iodine, that sort of thing. For this, bromine or chlorine should be fine, iodine would work as well. The thing we want to make sure we understand is how many carbons we have in our electrophile, and well, there are two here that we're adding on, so we're going to have two in our electrophile. So all we're going to do here is add on the leaving group. Let's say it's going to be bromine. So we have our two carbon, in fact, let me try and draw that again, that didn't come out too well. Let me just draw that again. We have our two carbon electrophile, and so these two are then going to react with each other. The positively charged carbon is going to get attacked by the negatively charged oxygen, breaking that bond and putting the electrons onto the leaving group. And if you follow that through, you'll find that this oxygen is bonded to this carbon, giving you your ether product. And that, in a nutshell, is the Williamson ether synthesis. So the species in step number 2 here that I haven't drawn on is simply an alkyl halide, and that's what that second species is always going to be, is an alkyl halide of some sort. However, it's not just any old alkyl halide this is going to be. We had this. Do you remember from your Organic 1 study again, if you have a strong nucleophile reacting with a primary substrate, so you got the leaving group all in one step, what sort of a reaction is that? Is it SN1 or is it SN2? Well, if you said SN2, you would be right. This second step in the Williamson ether synthesis is always an SN2 reaction, so you always want to make sure you have a primary alkyl halide here. This is actually important when you come to look at some applications of how we can use the Williamson ether synthesis to generate something. So we'll see that here in just a minute, but take a look at our two steps. Sodium hydride acting as the base, forming the alkoxide intermediate, which then reacts with the primary alkyl halide to form the ether, all the way starting from an alcohol. So let's look at an example of this and then ask ourselves, well, okay, take a look at this ether. We can tell it's an ether because of the oxygen with the two carbons either side of it. How are we going to use the Williamson ether synthesis to make this molecule? Okay. Now, the way to go about this is, if you remember when we went back here, we started off with an alcohol, and in our second step we attacked a primary alkyl halide with our alkoxide ion, which means that one side of the ether has to be a primary carbon. So look at the two carbons binding the oxygen here. This carbon's primary, as you can see. This carbon is secondary. It's the primary carbon that must have come from the alkyl halide. So therefore the secondary carbon, or the non-primary one, must have started from the original alcohol. So you can see in this case, all this bit on the left came from the original alcohol, and the bit on the right came from the alkyl halide. So the way to do this is we just look at the ether and see, well, which part is primary, and so that'll tell me which part came from the alkyl halide. Well, let's just see what we have. On the left-hand side we have this benzene ring, and when you look at this carbon here, you can see that carbon is definitely not primary, which suggests this would not be the alkyl halide. And let's look over at this carbon. Well, this carbon's connected to one more, so this carbon is primary. So therefore this bit here must have come from my alkyl halide. So therefore that means, if I draw out these carbons again, this is the carbon here that was bonded to the oxygen in the product. So this is the carbon that must have been bonded to a bromine in the first place. So in other words, this is what my alkyl halide must have looked like. And if that's what the alkyl halide looked like, then that presumably means then that the rest of the molecule, in other words the benzene ring, let me just draw this here, the benzene ring and the oxygen must have come from the original alcohol. And if this was originally an alcohol, it must have an OH here. So if this truly is the Williamson ether synthesis, okay, we would do our sodium hydride in our first step, which would make our alkoxide ion. Okay, our alkoxide ion is coming along here in just a minute, and it will look like this. That alkoxide ion, assuming that what we've done here is right, would then go and attack this carbon, kicking off that bromine, giving this product. So that's really it. Looking at the product and working backwards, we call this retrosynthetic analysis, to see how we got to our starting materials. But in this case, we're looking for which carbon coming off the oxygen is primary, because that determines which of those two parts of the molecule came from the alkyl halide in the second step. So our first step was addition of sodium hydride to our alcohol, in this case phenol, okay, the aromatic alcohol that you would have seen last semester. Then in the second step, that alkoxide ion reacted with that alkyl halide. Okay, in this case 2-methyl 1-bromopropane. Okay, so that in essence is the Williamson ether synthesis and how we can make unsymmetrical ethers.